Hello, everybody. Um, Today we're going to continue to learn the chapter one, um, the vectors. So in last class, we have learned something about the operations of vectors like addition, product, dot product, cross product, something like that. They're all operations for vectors. Um, Today, we're going to learn something about the differential calculus. Now, let's start today's lecture. So first, let's review a little bit about the most simple derivative or differential, which is the ordinary derivatives or a one-dimensional derivative. Suppose you have function of fx and it's a function f depends on one variable, which is x. So what is df over dx, or the derivative? So one thing we can draw here to make it more clear is, let's draw the fx, or the function over x. Maybe this is the function like this. Let's say this is the fx function. That's the curve of this function. So in the past, we have learned the df over dx, or the derivative, means the slope of this function at any points. Okay, let me make the screen a little bit bigger. Okay. For example, if you choose one x here, let's say this is x1, then the derivative of f at this point will be f prime x1. So the value of this f prime x1, or df dx at x1, will be the slope at this point for this curve. If you choose another point, for example here, x2, then the derivative of fx at this point will be the slope at this point. So that's the meaning of derivative for one-dimensional case. Remember that in this case, your function f, it depends on only one variable, which is x. So it's a function of x only. However, in this course, we're going to learn much more complicated functions. Most of the time, it's not a function of one variable, x. It's a function of three variables, x, y, and z. And in some other studies, maybe the function could be even more complicated, which has more than three variables. So first, let's take the three variable functions as example. Suppose now you have a function, let's say it's a temperature, which is T in this room, and the temperature in this room might be slightly different. Or if you don't think the temperature is very different in the different location in this room, we can extend perhaps the temperature function not only in this room, but in the whole building. Then you will figure out at different locations, the temperature might be different. For example, in the upper floors, the temperature might be higher. In lower floors, the temperature might be lower. If there's no air conditioners, of course. So even in a room, if you measure the temperature, if there's no air conditioners, still you can figure out when the position is higher, the temperature might be higher. When the position is lower, the temperature might be lower. So the temperature could be described in x, y, z coordinates for a room or a building or some space. So this is function. let's say T, XYZ, or temperature, depending on X, Y, Z coordinates in this room, is a temperature of three-dimensional or three variables. And then in the three-dimensional function, the derivative is a little bit more complicated. So here, the problem actually is not as bad as it looks. The theorem on partial derivative can describe how to calculate the derivative. So we define dt equals to partial dt over partial dx times dx plus partial dt partial y times dy plus partial t partial z times dz. So this is the definition of the derivative for a multi-dimensional function. For example, three-dimensional functions in x and y and z. So it can tell us how t changes when any of those three variables changes, either in dx direction or in y direction or dy, or the in z direction change, which is dz. Then you can calculate the change of the t. So now, if you look back, it's getting similar to the one-dimensional case of derivatives of one-dimensional function. Difference is now you have more variables, of course, in three dimensions. And here, this function or this equation could be written in another form, which is here. We can read it into a dot product of two vectors, which is partial dt over partial x in x direction, plus partial t partial y in y direction, plus partial t partial z in z direction, dot dx in x direction, dy in y direction, plus dz in z direction. Do you remember how to do the dot product for two vectors? If you remember, you will be able to calculate this, and then you will get exactly this function from here. Why do we want to write it in a more complicated way here? Because it will give you a lot of convenience and give you even a operator which can be used in the future. Now we can define the left part of this equation to be del t. We'll explain what is del operator and what is del t in the later slides. And in the right part of this equation, it could be described by dl. Do you still remember what is dl? In last class, we have explained, actually it's dr. It's the infinity small changes in the x, y, z coordinates. But usually we write this dr in dl. It's still a vector. It's a change of location. So now, the derivative of dt could be written in this way, and then we define del t as partial t partial x in x direction plus partial t partial y in y direction plus partial t partial z in z direction, which is called the gradient of t. Okay. That's the first concept we're going to learn in this class, the gradient. Note that del t is a vector because it has x, y, z directions or components. Okay, so let's start from here. And of course, based on the operation of dot product for two vectors, del t dot del t dot dl could be written in this way. Del t dot dl equals to the magnitude of del t times the magnitude of dl times cosine theta. Theta is the angle between del t and dl. And dt finally should be a scalar. Okay. And what's the meaning of del t? The gradient or del t points in the direction of maximum increase of the function t. So remember, function t, it's a three-dimensional function. So it has three variables, x, y, z. Del t or gradient is the direction of maximum increase of this function. Moreover, the magnitude of del t gives the slope or value of the slope along this maximum direction. So it's not very intuitive without any pictures or movies. So I will give you some links for two videos which will demonstrate those ideas better. So at the end of this class, you will see two links and you can check the videos from the links. It gives you more images and movies to show the ideas. For example, what does it mean? The gradient points in the direction of maximum increase of the function. And you will get much, much better idea than just reading those sentences. But it's okay. Now just keep it in mind, those concepts. Now, after we learn what is the gradient, let's do some real calculations. One example, find the gradient of r. R is square root of x squared plus y squared plus z squared, which is the magnitude of the position vector. Okay, so this is the example from the textbook. Now let's see how to solve it. So gradient, which means del r, means partial r, partial x in x direction, plus partial r, partial y in y direction, plus partial d r, partial z in z direction. So you need to do three calculations of derivatives. First, it's partial r, partial x. The partial r, partial x equals to 1/2 2x over square root of x squared plus y squared plus z squared. I guess from here to there, it's a little bit too much. Let's break it into several steps to help you understand how to do it. Okay, let's calculate partial r over partial x. Partial r is square root of x squared plus y squared plus z squared partial x. Sorry, it's a square root of x squared plus y squared plus z squared. So square root means to the power of 1/2. Then using the chain rule, we can calculate it as, first, let's take this x squared plus y squared plus z squared as a whole term or a sub-function. Then what we can do is we take the entire x squared plus y squared plus z squared as a whole term. Then you will have 1/2 times x squared plus y squared plus z squared negative 1/2 times partial x squared plus y squared plus, let me see, plus z squared over x using the chain rule. And then let's write it down here. So 1/2 times this term, this long term, to the power 1 negative 1/2 means the square root of x squared plus y squared plus z squared here times here partial, this term partial x, it should be 2x, then because it has in this x squared plus y squared plus z squared term, it has three components, which is x squared, y squared, z squared. So that's the sum of three terms. You could use the partial x squared over partial x plus partial y squared over partial x plus partial z squared over partial x. So only the partial x squared over x, it gives you 2x. For all the other terms, they're all 0 because y and z, they're not depending on x. So it's like a constant. So partial y to partial y squared over partial x, it's 0. The similar for the last term. So finally you get 2x. And then from here, you understand why you get this term in x direction. So similarly, you can get similar terms in y direction and z directions. And then finally, you can get the gradient in this way. So find the gradient is unit vector of r. So it says the distance from the origin increases most rapidly in the radial direction, and that's the rate of increase in that direction is 1. This is what we expect. Okay, let's do another example. Let's find the gradient of the following construction. So if you want to do it by yourself, please pause or stop the video and do it by yourself on a piece of paper. And then later on, you can continue this video to check if you're doing right. So now first, let me pause the video and waiting for you. Okay, now I suppose you have finished the calculation. If you want to double check your answer, you can continue to play this video. Now let's do it together. So the gradient of f, let's say partial del f x, y, and z equals to partial f partial x in x direction plus partial f partial y in y direction plus partial f over partial z in z direction. Let's calculate them one by one. So partial f to partial x, what's that? So partial df over partial dx, f is a sum of x squared plus y cubic plus z to 4. Y and z, they are independent from x. So when you do the partial f to partial x, you can consider y cubic as a constant. The similar for the z term, it's a constant to the x. So partial f partial x, you will get 2x in x direction. And for partial f partial y, in this case, y term, it's a function of y, it's y to power 3, but for x and z terms, they are constant if you consider y direction. So you have 0 plus partial y cubic, which will be partial y cubic partial y, which will be 3y squared. And then the last term, this term is 0, so in y direction, plus partial f partial z. In this case, the first and second term can be considered as constant. The derivative is 0. Then for the last term, you have 4z cubic in z direction. So that's the ingredient of this function. Did you do it correctly? Okay, so after we introduce the derivative, actually, after we introduce those calculations and the gradient, and now we can introduce this operator, which is Dow. We know the gradient of t equals to this, and then we can consider the left part in x, y, z direction as the operator, which is del. So del equals to partial over partial x in x direction plus y direction plus z direction. Here it writes this x and y and z unit vectors in the left of the partial operations, because it doesn't want you to think it's a partial x hat over partial x. That will result in a 0. So it writes the unit vector x and y and z on the left of the operation. But they're the same thing. No matter you write it in the left or right, it's the same thing. But sometimes if you write it in the right, it might be a little bit misleading sometimes. And del, its operator, it seems like a vector. It has x, y, z component, but it's a operator rather than a vector. So when you do something like this, del t, we don't consider it's a vector multiplied by a function. We consider it's an operator acting on the function, which is del t. So now let's see some operations for the del operator. It's very similar because the operator is very similar to a vector. For ordinary vector A, it can be multiplied in 3 ways. It can be multiplied by scalar, which is A, which is vector A multiplied by scalar A. It can be multiplied by another vector B in 2 ways: dot product A and B, or cross product A cross B. Correspondingly, there are the 3 similar ways of this operator del. It can be act in 3 ways. In the scalar function, for example, the temperature in the room, it's a scalar function of T. You can use del T. It results in the gradient of this scalar function. For a vector function V, what is a vector function? We're going to introduce a little bit of vector function in the later slides. For vector function V, it has 3 components: Vx, Vy, and Vz. So each component of this vector V is a function of x, y, z. So it's a complicated function. It has 3 components, and in each component, it's 3-dimensional. So for such a vector function, we can do um, dot product and cross product. So this is a dot product, del dot v. And here it's the cross product or cross operation, del cross v. And we call del dot v is the divergence, and del cross v is a curl. We will introduce divergence and curl in later slides. Now, let's see. First, the divergence. From the definition of del, we construct the divergence, which is del dot v. Del is the operator shown here, and v is a vector function shown here. Notice that this function has three components: x components, y components, and z components. In x components, it's vx. Vx itself, let's keep it in mind that Vx itself is a function. It's a scalar function, and it's a function of x, y, z. It's not a function of x. Instead, it's a function of x, y, z. Here, Vx simply means that's the x component of this three-dimensional vector function. It doesn't mean Vx here is a function of x only. Still, it's a function of x, y, z. So the geometrical interpretation is the divergence is a measure of how much the vector v spreads out or flows out. If we look at some examples, let's take A, B, C as examples. If we consider a point, let's say here, we will see there are vectors going out, going up, going down, going left, going right. So there are vectors going out. That means the divergence at this point is positive. Let's consider another point, let's say here. You will see there are some vectors points out and some other vectors points in, and the vector flow out and the vector flow in, they're at the same magnitude. So the divergence is 0. If we choose some points here, you will see there's some vectors flow out, some vectors flow in. However, the size of the arrows means the magnitude of the vectors. You'll figure out at any point, the vectors flow in is smaller than the vectors flow out. So still, there's still some net vectors flow out, means the divergence is still positive. Or in another way, a point of positive divergence is a source or faucet. A point of a negative divergence is a sink or a drain. For example, in picture A, if you opposite all the arrows to get into the point, then the divergence at this point should be negative because there are too many vectors. Their vectors flow in. Okay, now next. Okay, suppose the functions in those three figures are here, here, and here. So A, B, C, there's three functions. Let's calculate their divergence. Okay, so three functions. Let's just take one function as example. This is the first function. Now let's solve the example. It's very simple. Del dot VA, it is partial x, partial f, partial x, partial x, partial y, partial z, because the function is too simple. It's just x plus y plus z in each direction. So partial x over x, it's 1. partial y over partial y, it's a 1, and for the z direction, it's a 1. So finally, it's 3, means the divergence is 3. So similarly, for those two functions, you can calculate the divergence. Now, let's see some other examples. Calculate the divergence of the following vector functions. Okay, I'll give you some times to calculate, let's say, function A. Let's calculate divergence of the function A. I'll pause the video, and when you finish the calculation, please continue the video. Now let me pause it. Okay, now I suppose you finished. Now let's do the A question together. Del dot V A. Let's do just this function A equals to partial x squared. So first let's do this direction, and then let's do the y direction, which is partial, sorry, here it's partial x, partial y in, let's say, 3x z squared in y direction. Sorry, subtract. It should be subtract partial z 2x z in z direction. Now let's do the first term, partial x squared partial x. It should be 2x in x direction plus partial 3x z squared over partial y. So x and z, they are independent from y, so it's a constant in this derivative. So it should be 0 because that's a constant. If you do a derivative for constant, you get 0. Let's see the z direction. Okay, it's a negative. So let me write it in negative. So 2xz. So we consider 2x as constant. You will have 2x times z hat. So finally, this is your answer. 2x in x direction subtracted by 2x in z direction. So that's the divergence. So for B and C, you can do it by yourself. We just talked about the question A. Now let's see the curl. The curl is a cross product or cross operation of the del on an vector function. And as we said, the vector function is a function which contains 3 vectors, Vx, Vy, Vz. So either in Vx or Vy or Vz, you have 3 variables, which is x, y, z. Vx doesn't mean a function depending on x. It's still a function of x, y, z, but it's just x components of the vector function. So the cross product could be written in this way, as we introduced in the first class, and then you can read it in this term. So the geometrical interpretation is the curl means the measure of how much the vector v swirls around the point in question. For example, if you look at this picture, if you consider the points at the origin here, you will see the vectors, it swirls, and then the curl of the function at your chosen point shows us how much it swirls. And the direction, because now it's cross product of two vectors, so the result, it has a direction. So the direction is, let me see, the direction is going up. So the way to determine the direction is the right-hand rule. If you curl your fingers following the swirl of the vectors surrounding your chosen points, and your thumb will point to the direction of your curl. So similarly here, if you consider the points at the origin, if you calculate the curl of the function, you will see there's some vectors surrounding or swirl around the origin, and the curl describe how much it swirl, and the direction of this curl is going up too, based on the right-hand rule. Okay, so example. Now, if we have function which is shown here, let's calculate the curl. Okay, VA is here, so the curl is del cross VA. So we write first XYZ directions or unit vectors here, and then we write del components, and then we write the function VA components, and we calculate the determinant. Finally, after some calculations, you will get it's 2z. And here z is the unit vector in the direction. Here, it's another example. If you do the similar thing, you can get it in this way. So as expected, the curls point in the z direction, as we shown here by right-hand rule. Okay, so now we have introduced all the three. First, we introduce the del operator, and then we demonstrate three operations for the del operator. First, the gradient for a scalar function, then the divergence and cross or curl on vector functions. After this, let's introduce the product rules. The calculation of ordinary derivatives could be explained in the slides. So for example, you have the sum rule of the ordinary derivative. If you have two functions, f and g, and if you sum f and g, and if you want to calculate the derivative of the sum of f and g, then you get the derivative of derivative of f plus derivative of g. So the derivative of f plus g equals to the derivative of f and plus the derivative of g. So that's sum rule. And for multiplications, if it's multiplied by a constant, let's say k is a constant, f is a function, so dkf equals to the k times df dt. The product rule, if you have two functions, which is f and g, they both are functions of x, then dfg over dx equals to f dg dx plus g df dx. And the quotation and the quotient rule, which is shown here, df over g dx equals to g df dx subtracted by f dg dx over g squared. So this is the most complicated rule, but I suppose you have all learned it in calculus. So that's ordinary derivatives. Then we'll have similar operations for vector derivatives. First, sum. If you have del f plus g, it equals to del f plus del g. Del dot a plus b, a and b, they're all vector functions. It equals to del dot a plus del dot b. If you have del cross a plus b, then you get del cross a plus del cross b. That's the sum. And now let's see the scalar multiplication. If you have a function f, it's multiplied by k, then del kf equals to k del f. Similarly, del ka equals to k del dot product a. And similarly for the cross or the curl of the del operator. Okay. So the product rules are not quite simple. There are two ways to construct scalars as a product of two functions. For example, if you have two scalar functions, f and g, the product of f times g should be a scalar function. And if you have two vector functions, a and b, the dot product of those two vector functions, a and b, should be another scalar function. And there are two ways to make a vector function. For example, this is a scalar function f times vector function a, you get vector function, of course, or the cross product of two vector functions results in another vector function. Now let's see the del operators on those products. First, the gradient of fg equals to f gradient g plus f gradient, g gradient f. The del of a dot b equals to a cross del cross b plus b cross del cross a plus a dot del dot b plus b dot del a. It's difficult to remember that. However, those operations has been listed in the list of this book. Whenever you need to use it, you can check in the list. And there are some similar operations for divergence and for curls. So they're all shown in the slides and also in the list. And let's see the quotient rules. For three quotient rules, a scalar function over another scalar function, it could be written in this way. It's very similar to the ordinary, it's very similar to the quotient rule for ordinary derivatives. So another thing is dot product and then the cross product. So they're not very complicated. Please try to remember those. If you can't, you can check it in the list. And you can also refer to the slides or the textbook whenever you need to use it. Okay, so that's all the rules for the del operator for multiple functions. At the end of this lecture, I want to give you two links, which refers to two videos. Those two videos help you significantly to understand the whole lecture. It gives a lot of images and videos. Unfortunately, I'm not to make too much pictures or videos in my slides. However, go to these two videos. Go to these videos. It will give you a much better explanation for this lecture. Okay, so that's all for this lecture. I will see you next time. Bye-bye.